Hello everyone, I am Osmo Thakurel and today I am going to present a theorem from set theory that says for any sets A, B and C, the set difference of C and A union B is equal to the intersection of the set difference of C and A and the set difference of C and B. I know that is mouthful to say, but it is quite easy to understand. So let's begin. So in order to prove any theorem that contains equality, we have to go forward and backward. And what I mean is, so we have to prove that the first part, the left hand side, is a subset of the right hand side, and we have to do reverse. That is, the right hand side, whatever we have on the right hand side is also a subset of left hand side. If we do that, then we can prove this theorem. Now let's try to understand what this theorem says. So let's do it. Now let's talk about what it means that we are proving a subset. So if we are proving this first part is a subset of the second part, we have to show that any element that exists in this first part also exists in the second part. Basically, for example, if the whole thing has apollinate, the second part also should have apollinate, or whatever this thing has, this side also should have that one. So in order to that, let X and any element X is an element of this first part, which is the set difference of C and A union B. So now let's talk what it means, the set difference of C and A union B. Let's try to understand what this sign says. So this is what we call as set difference. And what it means is, so if we write, for example, if we write A set difference B, what this means is, if we have two sets A and B, then A set difference B means that we are talking about everything that is in A but not in B. So for example, in this case, since we are talking about X belongs to C set difference A union B, so that means we are talking about that X belongs to C but it does not belong to A union B. So if this first circle represents set C and if this second circle represents A union B, then X only belongs to this side. It does not belong to anywhere in A union B. So that is what I just wrote here. This means X belongs to C and X does not belong to A union B. Now let's try to understand what this second part means. So what does it mean by when we say X does not belong to A union B? So we normally write A union B as, we describe A union B as a set that contains every element that is in A or that is in B. So if these two are the sets A and B, then A union B basically means everything that is, that is either in A or that is in B, or both. So that is what we call as set A union B. And if someone says X does not belong to A union B, that is basically he is telling that X is lying somewhere else but not anywhere in A union B. So that means X does not belong to A and X does not belong to B. And that is what I just wrote here, which means X does not belong to A and X does not belong to B. So X belongs to C, but X does not belong to A and X does not belong to B. Now from this above sentence, we can see that X belongs to C and X does not belong to A. Let's group that together. Since we have X belongs to C and X does not belong to A, just like we talked about the set difference of C and A union B, this is also a definition of set difference. So by the definition of set difference, with this statement, we can say that X belongs to the set difference of C and A. So X belongs to C, but X does not belong to A. That is what we are basically talking about. Similarly, since we have x belongs to C and x does not belong to B from the above statements, we can write that x belongs to the set difference of C and B, since we just said x belongs to C and x does not belong to B. So now let's talk about why we are doing this. So in the right hand side we can see that there are like two different sets like grouped together by intersection, right? We have the set difference of C and A, and we have the set difference of C and B. So we are trying to like go towards the thing we have to show at the end. So we are just moving to this path. That is why we are grouping together x belongs to the set difference of C and A, and x belongs to the set difference of C and B. That is what we are basically doing. Now, when we put these things together, so we have x belongs to the set difference of C and A, and x belongs to the set difference of C and B. Now we have these two things. So if we put together these two things, we have x belongs to C, the set difference of C and A, and this x belongs to the set difference of C and B. Now let's talk about another terminology, that is intersection. So what intersection means is that if we have, let's say, A intersection B, and A and B are two sets, then intersection is something that the intersection like basically talks about the elements that is in both A and that is in B. So it means if something belongs to A intersection B, that means x belongs to A as well and x belongs to B. So it is this common part, x belongs to somewhere in this common part. Now in our context, since x belongs to C, x belongs to the set difference of C and A, and x belongs to the set difference of C and B, so since x belongs to these two parts, so it means that x belongs to the intersection of these two things, the set difference of C and A and the set difference of C and B. That means we just showed that for any arbitrary element x, if x belongs to this first part, the set difference of C and A union B, x belongs to the second part, that is the set intersection of the set difference of C and A and the set difference of C and B. So that is what we have to prove, right? So any element that belongs to the first part, that also belongs to the second part. So this first part is a subset of the second part. So that is just what I just wrote. Now let's move on the second part. Now let's do the second part of the job. So now we have shown that this first part is a subset of the second part. Now let's show that the second part is a subset of first part. That is how we prove the equality. Now let's begin. Now let's assume that any element x is in the set of intersection of the set difference of C and A and the set difference of C and B. So we know that by the definition of intersection, we know that x belongs to this part, which is the set difference of C and A, and x belongs to this part, which is the set difference of C and B. Now let's break that. Since we have x belongs to the set difference of C and A, and x belongs to the set difference of C and B, it follows the definition that x belongs to C and A means that x belongs to C, but x does not belong to A. Similarly, we have x belongs to C, the x belongs to the set difference of C and B, which means that x belongs to C but x does not belong to B. We have taught that x belongs to C and but x doesn't belong to A. In the same way, x belongs to C but x doesn't belong to B, right? So in total, we have x belongs to C, we have this in both sides, and we have x doesn't belong to A and x does not belong to B. So we have x belongs to C, and x doesn't belong to A, and x doesn't belong to B. So if we look at the definition of union, we see that since x does not belong to A and x does not belong to B, that means that x does not belong to A union B. So x does not belong to A and x does not belong to B. That is the definition, that by definition x does not belong to A union B. X does not belong to anywhere inside A union B. That is just what I just wrote. X does not belong to A union B. So we have x belongs to C. We have x belongs to C and x does not belong to A union B. Now again, by the definition of set difference, since we have x belongs to C and x does not belong to A union B, that means that x belongs to the set difference of C and A union B. So x belongs to C but x does not belong to A union B. Now we had begun from assuming that x belongs to this part, which is the intersection of the set difference of C and A and the set difference of C and B, and now we came to the conclusion that x belongs to the set difference of C and A union B, right? Now that is how we prove this part is the subset of this part, and that is just what I wrote. Now earlier we proved that this part is the subset of this part. Now we just proved that this right hand side is the subset of this left hand side. Therefore, we just proved the theorem. We just proved that the set difference of C and A union B is equal to the intersection of the set difference of C and A and the set difference of C and B. Thank you so much.